The darkness between the stars holds the universe's deepest secrets. We often picture space as a glittering tapestry of galaxies, but the cosmic void is something else entirely. It is not merely empty space, it is a realm of profound mysteries, a cosmic blank canvas where the rules of physics are tested and our understanding of reality is challenged. By the end of this journey, you will have explored 25 of the most baffling enigmas hidden within this vast emptiness. We will uncover voids so immense they defy logic and grapple with invisible forces that control the fate of the cosmos. What does the eerie silence of these great nothings tell us about our own place in the universe? This vast cosmic emptiness manifests most strikingly in a place astronomers call the Boötes Void. Named for the constellation where it resides, this region is also known as the Great Nothing, and for good reason. Picture a sphere of space so enormous it could take a beam of light 330 million years to cross from one side to the other. Within this incomprehensible volume, you would expect to find tens of thousands of brilliant galaxies. Instead, you find a profound scarcity, a cosmic desert where only a few dozen lonely galaxies dot the landscape. The standard model of the universe suggests matter should be distributed somewhat evenly, like a web. The Boötes Void is a gaping hole in that web, a void so immense its very existence challenges our understanding of how the cosmos assembled itself. How could such a nothingness come to be? One leading theory points to the very beginning of everything. Tiny, random fluctuations in the density of the primordial universe, magnified by the rapid expansion of cosmic inflation, could have created these vast empty pockets as space itself stretched. Other, more exotic ideas have been proposed. Could the void be the scar of a collision with a bubble universe from the greater multiverse? Perhaps the dark energy that accelerates the universe's expansion acts more forcefully in some regions, ruthlessly pushing matter apart. While the true origin remains elusive, the Boötes Void stands as a monumental question mark, a silent reminder that the largest structures in existence might be the great emptinesses between everything else. This cosmic desert is not truly empty. Even in the deepest voids, a ghostly presence makes itself known through its relentless gravitational pull. This is the enigma of dark matter. Its influence is felt everywhere, from the spin of galaxies to the very structure of the cosmic web, and the voids are no exception. We cannot see it, touch it, or interact with it through light, yet we know it is there because of the way it bends space and tugs on the things we can see. Within a void, the gravitational effects are subtle but profound. The few galaxies that do exist are moving in ways that suggest they are being pulled by an immense, unseen mass. It is as if the void itself is lined with an invisible scaffold, a framework of dark matter that dictates where luminous matter can and cannot gather. Without this unseen architecture, the universe as we know it would simply fly apart. So what is this mysterious substance? The leading candidates are as elusive as they are fascinating. One possibility involves weakly interacting massive particles, or WIMP. These are theoretical heavy particles that barely interact with normal matter, passing through our planet and even our bodies by the trillions every second without a trace. Another candidate is the action, an incredibly light particle born from theories attempting to solve other fundamental puzzles in physics. Both would be remnants from the universe's fiery first moments, frozen in time and now forming a vast, invisible ocean throughout the cosmos. The hunt for these phantom particles is one of science's greatest quests. To escape the constant interference of cosmic rays and other noise, detectors are placed deep underground in abandoned mines or beneath mountains. There, in the profound silence and shielded by thousands of feet of rock, scientists wait for the once-in-a-lifetime ping that might signal a dark matter collision. Other experiments look to the skies, searching for indirect signals like the unique light that might be produced if two dark matter particles were to annihilate each other in the depths of space. For decades, this search has yielded nothing but tantalizing hints and frustrating silences. Why does this substance, which seems to form the very backbone of the cosmos, so utterly refuse to reveal itself? The answer may lie not in the crowded galaxies, but in the profound emptiness of the voids themselves. This relentless expansion, driven by the void's own emptiness, points to an even deeper force at work. Dark energy is the name we give to the mysterious phenomenon causing the universe's expansion to accelerate. It is not merely pushing galaxies apart, it is stretching the very fabric of space-time, and this effect is most potent where there is the least matter to resist it. Inside a cosmic void, dark energy operates unchecked. These vast, empty regions are not static, they are actively growing, becoming larger and more profound as the eons pass. Think of the universe as a rising loaf of raisin bread. The raisins are galaxies, and as the dough expands, all the raisins move apart. But in the vast, empty stretches between the raisins, the dough itself is stretching fastest of all. Over billions of years, time-lapse simulations show these voids swelling, merging, and consuming the thin filaments of the cosmic web, accelerating the universe toward a colder, lonelier future. So what is the engine behind this great acceleration? One of the oldest ideas is the cosmological constant, a concept even Einstein considered. This proposes that dark energy is an inherent property of empty space itself. The vacuum of nothingness, according to quantum physics, is not truly empty but seethes with virtual particles flickering in and out of existence. This quantum fizz could generate a constant, repulsive force that drives the cosmos apart. Yet there is a problem. The amount of energy predicted by this theory is astronomically larger than what we observe, a discrepancy so vast it is one of the worst predictions in all of physics. This has led scientists to consider more dynamic possibilities, like a cosmic field called quintessence. Unlike a constant force, quintessence is a dynamical energy field that could change over time, perhaps weakening or strengthening, and could even interact with matter in subtle ways. Is the force tearing the cosmos apart a fixed feature of reality, or is it a shifting, evolving entity? The answer may be written in the growing emptiness of the voids, a slow motion clue to the ultimate fate of everything. But the emptiness of these voids hides another profound cosmic puzzle, one that concerns the very stuff you and I are made of. Astronomers call this the missing baryon problem. Baryons are the particles that make up all the ordinary matter we see, from stars and planets to our own bodies. When we tally up all the baryons that should exist based on our models of the Big Bang, we come up short. A significant portion of the universe's normal matter is simply unaccounted for. This missing matter is not dark matter, it is the atoms and gas that should be visible but are not. The problem is particularly acute within the cosmic voids. We can count the matter in galaxies, but what about the vast expanses in between? The leading suspect is a ghostly, diffuse fog of superheated gas known as the warm-hot intergalactic medium, or the WIM for short. This is not a cold, dark emptiness, but a searingly hot, thin plasma woven through the voids and the cosmic web. The challenge is that this gas is so incredibly diffuse and so hot that it is nearly invisible to our telescopes. It does not glow brightly like a star, it only betrays its presence under very specific conditions. How do you find something that is almost nothing? Scientists have had to become cosmic detectives looking for subtle clues. One method is to watch as the light from a distant, brilliant quasar passes through the cosmic web on its journey to Earth. As this light travels through the WIM, certain elements in the gas, like highly charged oxygen, will absorb very specific wavelengths of light, leaving a faint fingerprint in the quasar's spectrum. It is like detecting a distant, invisible fog by the way it dims the light of a single, faraway street lamp. Another technique involves looking for a faint glow of X-rays that this hot gas might emit, a whisper of heat against the cold backdrop of space. Finding this missing matter is crucial because it completes the inventory of our universe. Without it, our understanding of cosmic structure is fundamentally incomplete. These vast, seemingly empty voids may not be empty at all. They may be filled with a thin, hot ocean of atoms, the final resting place of the universe's lost material. This profound emptiness forces a difficult question, one that echoes through the silent expanse. If the universe is so vast and so old, why does it feel so utterly deserted? The cosmic void presents a paradox. We look out across billions of galaxies, each with billions of stars, and the mathematical probability for other intelligent life seems overwhelming. Yet when we listen, all we hear is a deafening silence. This is the heart of the Fermi Paradox, and these vast voids might be central to the mystery. They could represent cosmic dead zones, regions where the conditions for life were never right, or where any spark of civilization was ultimately snuffed out. One chilling explanation is known as the Great Filter. This theory suggests that somewhere between the emergence of life and the colonization of the galaxy, there exists a barrier, a challenge so immense that almost no civilization survives it. This filter could lie in our past, a rare fluke that allowed life to begin at all. Or, more ominously, it could await us in our future. Perhaps every technological civilization, upon reaching a certain stage, discovers something or creates something that leads inevitably to its own destruction. The silent voids could be the graveyards of civilizations that failed to pass this test. Another possibility is that intelligent life is simply too rare. The cosmic voids might be the norm, not the exception. The complex chain of events needed for a technological species to arise, the perfect star, the right planet, stable planetary conditions for billions of years, might be so unlikely that civilizations are isolated islands in an endless, empty sea. Or perhaps we are not listening correctly. An advanced civilization might not use radio waves, a technology we have barely mastered. They might communicate through neutrinos or manipulate space-time itself with gravitational waves, methods we are only beginning to dream of. Their signals could be washing over us right now, indistinguishable from the background hum of the cosmos. As we peer into the deepest, darkest voids, their starless horizons reflect our own profound solitude. Are we the first to gaze into the abyss and ask these questions, or are we simply alone in the grandest sense? The silence itself may be the answer. This profound silence is echoed by a different kind of cosmic whisper, one frozen in time from the very dawn of the universe. Embedded within the faint glow of the cosmic microwave background, the afterglow of the Big Bang itself, lies a chilling anomaly known simply as the cold spot. It is a vast circular region, significantly colder than its surroundings, stretching across 1 billion light-years. Think of the cosmic microwave background as a baby picture of the cosmos, a nearly uniform snapshot of the universe when it was just 380,000 years old. Most variations in this ancient light are tiny, random fluctuations, but the cold spot is different. It is too large and too cold to be easily explained by our standard models of cosmic inflation, the period of rapid expansion that shaped the early universe. One compelling theory links this frigid patch to a supervoid, an immense emptiness in the modern universe lying in the same direction. The idea is that as light from the cosmic microwave background travels through such a void, it loses energy climbing out of its gravitational well, a phenomenon known as the integrated Sachs-Wolf effect. This would make the light appear cooler to us. The problem is that the observed cold spot is far colder than any known supervoid should produce. This discrepancy suggests that either the void is far larger and emptier than any we have ever catalogued, or our understanding of gravity and cosmic expansion on the largest scales is fundamentally flawed. If this spot is indeed a shadow cast by a void, it challenges the very foundations of our cosmic timeline. What could have created such a profound emptiness so early on? Some physicists propose a far more exotic origin, a relic from the universe's violent birth known as a cosmic texture. This would be a knot or a defect in the very fabric of space-time, a frozen-in scar from a phase transition in the primordial cosmos. As the universe cooled and expanded, its fundamental forces may have separated in a way that left behind these tangled regions, with the cold spot being the imprint of one such cosmic unraveling. An even more radical idea suggests the cold spot is a bruise, the remnant of a collision between our universe and a bubble of another universe in the wider multiverse. In this scenario, the energy released by such a cosmic crash could have left a permanent cold imprint on our sky. Detailed maps of the cosmic microwave background highlight this enigmatic region, a stark blue patch against the warmer reds and yellows of the rest of the ancient light. It stands as a cosmic fossil, a billion light-year-wide question mark challenging us to choose between an impossibly large void, a crack in space-time, or a mark from another reality entirely. The profound isolation of a cosmic void does not just shape emptiness, it also forges the galaxies trapped within it into strange and solitary forms. Far from the bustling crowds of galactic clusters, a void galaxy lives a life of quiet desperation. These islands of stars are often described as red and dead. They have exhausted their supply of cool gas, the raw material for new stars, and their vibrant blue, star-forming youth has faded into a dull, crimson glow of aging stellar populations. They are the cosmic equivalent of a ghost town where the factories have shut down and the lights are slowly going out. Picture the difference side by side. In a dense cluster, a majestic spiral galaxy like our own Milky Way spins gracefully, its blue-tinged arms alive with the fierce light of newborn stars. It is constantly fed by streams of intergalactic gas and occasional interactions with neighbors, a vibrant city in a cosmic metropolis. Now shift your gaze to a void. Here, a lone elliptical galaxy hangs motionless, a fuzzy, reddish ball of ancient stars. It is a hermit cut off from the cosmic supply chain, its star-forming fuel either consumed long ago or stripped away by the void's own unique physics. This galactic solitude has a profound effect on its very structure. The geometry of the void itself, a vast matter-poor expanse, shapes the magnetic fields that permeate the space between galaxies. In denser regions, the turbulent motions of gas and the constant dance of galaxies can amplify and tangle these fields. But in the quiet depths of a void, the intergalactic magnetic fields are likely weaker, more ordered, and stretched over immense, placid volumes. This calm environment means there is less turbulence to compress gas clouds and trigger the collapse that births new stars. The galaxy is left to stew in its own stillness, its internal gas reservoir slowly heated by supernova explosions or the supermassive black hole at its core until it becomes too hot to condense. The very emptiness that defines the void becomes a self-reinforcing prison for the galaxies within it, ensuring they remain red, quiet, and alone. How does a galaxy's address in the cosmos determine its entire life story? The void holds a stark answer, showing us that in the universe, location is everything, and the deepest solitude can be a sentence to a slow, cosmic fade. This cosmic solitude even dictates the direction in which a galaxy spins. At the very boundaries of these voids, where the emptiness gives way to the filaments of the cosmic web, astronomers have observed something deeply strange. The spin axes of these lonely galaxies are not randomly oriented. Instead, they appear to be aligned with the curved surface of the void itself, as if the galaxies are rolling along the inner walls of a vast spherical chamber. This is not what we would expect if the universe were truly isotropic, meaning the same in all directions. The standard assumption has long been that on the largest scales, the cosmos is a chaotic, random place with galaxies pointing every which way. This alignment challenges that fundamental idea, suggesting the universe has a hidden grain, a preferred direction imprinted upon it from the very beginning. So what cosmic hand could be guiding these galactic spins? One of the most profound possibilities points all the way back to the first instance after the Big Bang. In that seething, nascent universe, the rapid stretching of space known as inflation may have generated ripples in spacetime itself, called primordial gravitational waves. These waves would have been frozen into the fabric of the cosmos, creating a subtle, underlying pattern that influenced how matter first began to clump together. Billions of years later, this faint primordial whisper could still be dictating the rotation of galaxies along the edges of the great voids. Another potential architect is the cosmic magnetic field. While incredibly weak, these vast magnetic fields that stretch between galaxies could have been amplified by the unique, quiet environment of the voids. As galaxies form and move, their gas could be shaped by these magnetic lines of force, slowly coaxing their spins into alignment over eons. The evidence for this comes from painstaking work with massive sky surveys. Projects like the Sloan Digital Sky Survey have mapped the positions and rotations of millions of galaxies. By analyzing this immense dataset, scientists can statistically determine the direction a galaxy is spinning relative to its position on the void's edge. The results are not absolute, but the statistical signal is there, a subtle trend that defies random chance. Yet this discovery is far from settled science. The astrophysics community is deeply engaged in debate. Is the signal real, or is it a trick of the data, a selection bias in how we observe these distant objects? Could other, more local gravitational effects be responsible for the perceived alignment? The very methods used to measure galaxy rotation are indirect and complex, adding another layer of uncertainty to the mystery. If these alignments are confirmed, they force us to rewrite our cosmic story. The universe is not just a collection of random structures, but a place where the largest emptinesses exert a ghostly influence on the galaxies that border them, a silent dance choreographed at the dawn of time. What other hidden patterns are written across the sky, waiting for us to see the universe not as chaos, but as a composition? Deep within the cosmic void, a different kind of messenger occasionally tears through the silence, carrying an energy so immense it defies belief. These are ultra-high-energy cosmic rays, subatomic particles racing across the universe with energies millions of times greater than anything produced in our most powerful particle accelerators. A single one of these particles, often just a solitary proton, can carry the kinetic energy of a professionally thrown baseball, all compressed into a speck smaller than an atom. When such a particle slams into Earth's atmosphere, it does not arrive quietly. It initiates a spectacular cascade, a sprawling shower of billions of secondary particles that rain down over an area the size of a city, all born from a single, unimaginably powerful collision with an air molecule. Yet for all their ferocity, these cosmic bullets present a profound mystery. When we trace their paths back across the universe, some appear to originate not from brilliant galaxies or violent explosions, but from the deep, dark emptiness of the cosmic void. How can nothingness be the source of such incredible power? The journey to answer this is fraught with difficulty. These particles are not like beams of light that travel in straight lines. They are charged, which means they are whipped and bent by the magnetic fields that fill the space between galaxies. It is like trying to trace the path of a pinball ricocheting through an immense, invisible maze. By the time one of these rays reaches us, its original direction has been scrambled beyond easy recognition. We know it came from somewhere in a vast, fuzzy patch of sky, but the precise source is lost. This magnetic deflection is the primary reason the origin of these rays remains one of astrophysics' most stubborn puzzles. So what cosmic engines could possibly launch them? The usual suspects are the most violent events we know: an active galactic nucleus where a supermassive black hole feasts on surrounding matter, can generate jets of plasma stretching for thousands of light years. These jets are natural particle accelerators on a cosmic scale. Similarly, the catastrophic collapse of a massive star into a gamma ray burst releases more energy in a few seconds than our Sun will in its entire 10 billion-year life, a blast that could easily fuel these cosmic projectiles. But when the arrival direction points to a void where such brilliant, energetic objects are exceedingly rare, we are forced to consider more exotic possibilities. Could the source be something we cannot see at all? One hypothesis points to the decay of super-heavy dark matter particles. If such particles were to spontaneously decay in the empty depths of a void, they could release their immense mass energy, creating a burst of ordinary particles, including these ultra-high-energy protons. Another, even more speculative idea involves cosmic strings. These are theoretical, flaw-like defects in space-time, unimaginably thin yet incredibly dense, left over from the universe's first moments. The immense energy stored in a vibrating cosmic string could be the ultimate particle accelerator, flinging matter across the cosmos with ease. The silent void, it seems, may not be empty of events, but only empty of the light by which we normally see them. Each ultra-high-energy cosmic ray that streaks out of the darkness is a clue, a calling card from a hidden, violent process we are only beginning to imagine. The same emptiness that births ultra-high-energy particles might also hold a signature from beyond our own reality. One of the most profound theories in cosmology suggests that cosmic voids are not mere accidents of our universe, but the scars of ancient collisions with other universes entirely. This idea emerges from the theory of eternal inflation, a model for the Big Bang's explosive beginning. Imagine our entire cosmos as one bubble in a vast, frothing cosmic foam, where new universe bubbles are constantly budding off from an eternally expanding parent space. In this infinite multiverse, it is statistically inevitable that these budding bubbles would sometimes bump into one another. When our universe was young and its space-time still malleable, a collision with a neighboring bubble universe would have been a cataclysmic event. The energy released at the boundary would have been imprinted onto the fabric of our cosmos, potentially creating a vast region of lower density, a void, as the two distinct realities pushed each other apart. The shockwave from such an impact could have left a detectable signature, not only in the distribution of galaxies and voids we see today, but also as a distinct cold or hot spot in the cosmic microwave background. The enigmatic cold spot we discussed earlier is a prime candidate for just such a cosmic bruise. While other explanations exist, the multiverse collision theory offers a breathtakingly elegant, if speculative, solution. Scientists take this idea seriously enough to search for its evidence. They run complex computer simulations to model what such a bubble collision would look like on a map of the CMB, searching for specific patterns, like a series of concentric rings of temperature variation that would be hard to explain by any other means. They also analyze the three-dimensional map of galaxies and voids, looking for unusually shaped or arranged emptinesses that might trace the outline of an impact zone. The scientific credibility of this search hinges on prediction and falsification. If a specific, testable pattern predicted by the multiverse model is found and confirmed, it would be the first tangible evidence that our universe is just one among countless others. Visualizing this is a challenge for the imagination. Animated simulations show our universe not as a lonely island, but as a shimmering sphere adrift in a sea of other, equally vast spheres. As two bubbles drift closer, their boundaries touch, and a ripple of unimaginable energy propagates inward, permanently warping the interior structure of both worlds. The resulting void would be a fossilized borderland, a place where the laws of physics as we know them might subtly differ. This transforms the great cosmic voids from mere empty spaces into potential windows. If we could peer deep into the heart of the largest void, would we be looking at the faded imprint of another cosmos? The search for an answer is a gamble on the grandest scale, probing the deepest emptiness for proof that we are not alone in the ultimate sense. While the rest of the universe evolves in a frenzy of collisions and star birth, the cosmic void remains a sanctuary of stillness. This profound emptiness functions as a cosmic time capsule, preserving conditions that have long since vanished from the crowded galactic clusters. In the dense urban centers of the universe, gravity has orchestrated a complex history of mergers, galactic cannibalism, and multiple generations of stars, effectively erasing the original signature of the primordial cosmos. But in the deep voids where galaxies are few and interactions are rare, the environment remains relatively pristine. It is a backwater, a place where the ancient ways of the universe are frozen in time. Here we might find the clearest records of the first stars and the great transformation known as the epoch of reionization. This was the moment when the first brilliant sources of light, thought to be massive, short-lived stars, flooded the universe with ultraviolet radiation, burning away the fog of neutral hydrogen that filled all of space and making the cosmos transparent to light for the first time. The key to understanding this cosmic dawn may lie in the dwarf galaxies that drift like lonely ghosts within the voids. Unlike their larger cousins, these small, faint galaxies are believed to be relics from the early universe, systems that formed their stars long ago and have remained largely unchanged ever since. They are living fossils, and by studying their composition and the gas that surrounds them, astronomers can effectively look back in time. They search for the chemical fingerprints of that first generation of stars, which were composed almost entirely of hydrogen and helium. When these primordial giants exploded as supernova, they forged the first heavy elements like carbon and oxygen, and seeded the cosmos with the building blocks for future planets and life. The pristine gas within a void, untouched by later generations of pollution, should hold a pure record of that first chemical enrichment. But how do you observe something so faint and so far away? The technical challenges are immense. These dwarf galaxies are incredibly dim, and the primordial gas clouds are diffuse and do not emit their own light. Scientists must rely on the most powerful telescopes and ingenious techniques. They use the light from distant quasars as cosmic flashlights. As this brilliant beam passes through a void galaxy or a cloud of primordial gas on its journey to Earth, the gas absorbs specific wavelengths of light. This creates a unique barcode of absorption lines in the quasar's spectrum, revealing the composition, temperature, and density of the invisible material it passed through. It is an incredibly difficult observation, like trying to analyze the chemistry of a distant, invisible fog by the specific way it dims the color of a single star billions of light years away. Visualize the difference. On one side, a vibrant, modern galaxy cluster teems with brilliant spirals and ellipticals of all colors, a testament to billions of years of cosmic evolution. On the other side, a vast, dark void holds only a few faint, reddish smudges, the dwarf galaxies floating in a sea of ancient, unpolluted gas. This stark contrast is what makes the void so precious. It is not just an empty space, but a window into the universe's infancy, a silent archive holding the secrets of our deepest origins. What other ancient stories are written in the faint light of these isolated islands, waiting for us to learn how to read them? Our galaxy is not drifting aimlessly through the cosmos. It is on a journey, pulled by invisible forces on a scale that defies easy comprehension. For decades, astronomers have known that our entire local group of galaxies, including the Milky Way, is racing toward a specific point in the sky at a staggering 2 million kilometers per hour. The primary source of this immense pull is a gravitational anomaly known as the Great Attractor, a dense region of space hidden behind the dust and stars of our own galactic plane. But the full story is more complex and far more intriguing. Our motion is not just a result of what is pulling us, but also of what is pushing us. The other half of this cosmic equation is a profound emptiness called the dipole repeller. This is a vast cosmic void, an underdense region so immense that its lack of gravitational pull acts as an effective push. Think of it like being in a boat on a wide river. You are drawn toward a powerful waterfall downstream, the Great Attractor, but you are also being pushed from behind by the current flowing away from a shallow, empty basin, the dipole repeller. It is the combination of this pull from the dense mass and this push from the great void that sets our precise course through the universe. Mapping this cosmic flow required a radical shift in perspective. Instead of just looking for concentrations of light, astronomers had to chart the motions of thousands of galaxies. They painstakingly measured their distances and velocities, creating a three-dimensional flow diagram of our local universe. The resulting map is breathtaking. It shows our local group as one point in a vast river of galaxies, all streaming toward the same gravitational basin. But when scientists calculated the pull from all the visible matter in the Great Attractor, they found it was not enough to account for the speed of this flow. Something was missing. The key was to account for what was not there. The dipole repeller, a volume of space with far fewer galaxies than average, creates a gravitational hill. Just as water flows away from a high point, galaxies flow away from an underdense void. Our motion is the direct result of this imbalance. We are sliding down the cosmic slope from the void and toward the attractor. This discovery fundamentally changed our understanding of the cosmic web. It proved that the great voids are not passive backgrounds. They are active players in the dynamics of the universe, their emptiness wielding a gravitational influence that shapes the paths of galaxies. The ongoing effort to understand the full mass distribution now combines these maps of galaxy motions with surveys of the faint, hot gas of the warm-hot intergalactic medium and models of dark matter. We are slowly learning to read the universe not just by its light, but by its silence and its motion. What other unseen currents are carrying us through the darkness, guided by the push and pull of nothingness itself? This profound push and pull is orchestrated by an invisible force woven through the emptiness itself. The vast expanses of cosmic voids are threaded with magnetic fields, ghostly lines of force that permeate the near-perfect vacuum. These are not the strong, localized fields of a star or a planet, but something far more diffuse and ancient. Their origins likely stretch back to the universe's infancy, to a time before the first stars flickered on. In those primordial moments, weak seed fields could have been generated by the turbulent plasma of the Big Bang or by the first quantum fluctuations. Imagine these initial fields as impossibly faint whispers, a subtle texture in the fabric of space-time. For these whispers to persist and grow across billions of light years, they needed a mechanism to amplify them. This is where the unique dynamics of the cosmic void come into play. While the void is mostly empty, it is not completely static. The slight motions of the sparse ionized gas and the overall expansion of the void itself can stretch and shear these magnetic field lines. Think of it like pulling on a tangled slinky. As the void grows, it draws the field lines out, making them longer and more organized. This process, over cosmic timescales, can transform a chaotic, weak seed into a coherent, large-scale magnetic field that blankets the entire void. These faint fields, though weak, may play a crucial role in the cosmos. They could provide the initial nudge that guides gas flows during the formation of a galaxy, setting the stage for its future spin. They also act as a cosmic maze for high-energy particles. When an ultra-high-energy cosmic ray travels through a void, these magnetic fields bend its path, scattering its trajectory and making its true point of origin a mystery. This is why tracing these rays back to their sources is so profoundly difficult. The void's magnetic field is the invisible hand that scrambles the cosmic signals. Measuring such an ethereal force is one of astronomy's greatest challenges. How do you detect a magnetic field 1,000,000 times weaker than Earth's, stretched across millions of light years of nothing? Scientists rely on indirect but ingenious methods. One technique involves observing the light from distant radio galaxies. As this light travels through the magnetized void, its polarization or the orientation of its light waves can be subtly rotated. This effect, known as Faraday rotation, leaves a tiny fingerprint on the radio signal, a fingerprint that betrays the presence and strength of the magnetic field it passed through. It is an incredibly delicate measurement, like trying to detect a gentle breeze by watching how it twists the light from a faraway candle. Another method looks for the faint synchrotron radiation that electrons would emit as they spiral along these magnetic field lines. This would create a faint, diffuse glow across the void, a whisper of light that has never been detected but is hunted relentlessly. The very existence of these vast magnetic fields raises a profound question. Are they a relic from our universe's first second, a fossil frozen into the cosmos during its birth? Or were they forged later by the first generation of stars and galaxies, whose winds and explosions then seeded these fields into the void? The answer is written in the silent, magnetized emptiness, a hidden layer of cosmic structure that guides the fate of matter and energy alike. What other invisible architectures are we floating through, completely unaware of their subtle, universal influence? The profound silence of the void is not always unbroken. Sometimes the only sign of a cataclysm is a single, rhythmic pulse tearing through the darkness. When a massive star dies alone in the depths of a cosmic void, its death is a quiet, private affair. There is no neighboring star to witness the final, furious collapse. With a gravitational sigh, the star's core crumples under its own weight. If the remnant is dense enough, it becomes a neutron star, a city-sized object with the mass of a sun, its matter compressed to the point where atoms cease to exist. Should the collapse be even more extreme, it forges a black hole, a point of infinite density where gravity is so strong that not even light can escape. These are the ghosts of dead stars, and in the emptiness of a void, they become perfect phantoms. A lone neutron star, cold and dark, is virtually undetectable across the vast intergalactic distances. It is only under specific, rare circumstances that it reveals itself. If it spins rapidly, beaming out radiation from its magnetic poles like a cosmic lighthouse, we call it a pulsar. We can detect its precise, clockwork flashes as the beam sweeps past Earth. Similarly, a solitary black hole is a perfect cloak of darkness unless it is actively feeding. Should a wisp of the void's sparse gas drift too close, the black hole's immense gravity can shred it, heating the material into a glowing, swirling accretion disk before it crosses the event horizon and vanishes from our universe. That faint, final glow is the only tombstone such an object will ever have. This leads to a staggering possibility. The cosmic voids could be haunted by a vast, unseen population of these dark remnants. Every massive star that formed in the sparse galaxies of the void over billions of years has faced this fate. Their numbers could be immense, a hidden archipelago of stellar corpses drifting in the dark. Could this population account for some of the universe's missing baryonic matter? While they are unlikely to solve the entire missing mass problem, these isolated neutron stars and black holes represent a significant portion of ordinary matter that has effectively vanished from our view, retreating into near-perfect obscurity. Visualize a lone pulsar, its twin beams of radiation cutting through the eternal night, a metronome ticking for no one in an ocean of nothing. Or picture a black hole, its faint accretion disk a mere ember in the overwhelming dark, a silent engine consuming the last traces of its isolated existence. These are not the brilliant, chaotic deaths seen in crowded galactic arms, but a slow, cold fade into finality. They are the ultimate endpoints for stars born in solitude, their entire life cycle defined by the emptiness that surrounds them. How many of these dark sentinels are drifting in the void, their immense mass leaving only a gravitational whisper as evidence of their passing? These ghostly remnants drifting in the void present a gravitational puzzle of their own, one that challenges our most fundamental understanding of the cosmos. Einstein's theory of general relativity has been our guide to the universe for over a century, perfectly predicting the orbit of Mercury and the bending of light around massive stars. Yet in the profound emptiness of cosmic voids, where the gravitational influence of matter is almost negligible, some scientists believe this foundational theory might reveal its first cracks. The extreme low-density environment of a void acts as a unique laboratory, a place where the subtle effects of gravity are not drowned out by the roar of crowded galactic clusters. Here, the rules themselves might be different. The most prominent challenge comes from the observed motions of galaxies, both within clusters and in isolation. For decades, we have known that galaxies rotate so quickly that they should fly apart. The visible matter in a spiral galaxy, all its stars and gas, simply does not provide enough gravitational glue to hold it together. Our solution has been to invoke the unseen hand of dark matter, a mysterious substance whose gravity provides the extra pull. But what if we are interpreting the signal incorrectly? A competing idea, known as modified Newtonian dynamics or MUND, proposes a different answer. It suggests that on very large scales, where accelerations are incredibly faint, the force of gravity does not follow Newton's or Einstein's laws precisely. Instead, it becomes stronger. In this view, there is no missing dark matter. The strange rotation of galaxies is simply gravity acting as it always does in a regime we have never properly tested until now. The cosmic void is the ultimate testing ground for this radical idea. Within these vast, empty regions, the accelerations are the lowest in the universe. If MUND is correct, the few isolated galaxies wandering the void should exhibit very specific and peculiar dynamics, their rotation curves and movements differing distinctly from the predictions of general relativity coupled with dark matter. Scientists are now using massive sky surveys to study these lonely void galaxies, measuring their rotation and their trajectories with immense precision. The initial results are fiercely debated. Some analyses suggest the motions of void galaxies align more closely with MUND predictions, as if the modified force of gravity is more apparent where the cosmic background density is lowest. Other studies find no such discrepancy, firmly supporting the standard model of dark matter. The debate hinges on incredibly subtle measurements and complex statistical analyses of thousands of galaxies. The evidence is not yet clear enough to declare a winner, but the very existence of the debate proves the void's value. It forces us to question our assumptions in an environment where the rules are pushed to their limits. Visualize a comparison. On one side, a simulation based on general relativity and dark matter shows void galaxies moving under the influence of an invisible, pervasive halo. On the other, a MUND simulation shows the same galaxies governed by a tweaked law of gravity with no dark component at all. The differences in their predicted paths are subtle, but for cosmologists, they represent a fork in the road for our entire understanding of physics. Is the cosmos filled with an invisible substance we cannot find, or have we been misreading the force that binds it together since the very beginning? The silent, empty voids may hold the answer, serving as the ultimate arbiter in a conflict that reaches to the very heart of physical law. Our map of the cosmic web might be an illusion, a grand trick of light and time. The very emptiness we observe could be a phantom, a cosmic mirage created by the relentless expansion of the universe. This is the puzzle of phantom voids, regions that appear profoundly underdense to our telescopes but may, in reality, be far less empty than they seem. The culprit is a subtle but powerful relativistic effect, one that warps our perception of distance and scale on the grandest stage imaginable. When we peer into the depths of space, we are also looking back in time. The light from a galaxy at the near edge of a void left its source millions of years before the light from a galaxy at the far edge. During that immense journey, the universe has continued to expand, stretching the very fabric of space between those 2 points. This means we are not seeing the void as it is now, but as a composite image from different cosmic epochs. The Alcock-Paczynski effect exploits this fact. It describes how we can be fooled when measuring the shape and size of these vast structures. Imagine a spherical void. If we assume a certain fixed rate of cosmic expansion to calculate the distances to its boundaries, the relativistic stretching of space can make this sphere appear distorted to us, like a circle viewed through a warped lens. It might look elongated along our line of sight or squashed, depending on the true nature of dark energy driving the expansion. We measure its dimensions using two different rulers. One ruler is its angular size, how big it appears on the sky. The other is its depth, measured by the redshift or stretching of the light from galaxies within it. If our underlying model of cosmic expansion is incorrect, these two measurements will not agree, and we will misjudge the void's true physical size and emptiness. A void that seems colossal and profound might be a much smaller, shallower depression in the cosmic density. This is not just a minor mapping error. It strikes at the heart of our quest to understand dark energy. We use giant voids as standard rulers. By measuring their apparent sizes at different distances and therefore different times in cosmic history, we can trace how the rate of the universe's expansion has changed. But if we cannot tell a real void from a phantom, our measurements of dark energy become uncertain. Is the acceleration of the cosmos constant, or is it changing? The answer depends on knowing whether the great voids we see are true emptiness or relativistic ghosts. Visualizing this would show a single, spherical void from the perspective of two different cosmic histories. In one where dark energy behaves as a simple cosmological constant, the void appears as a perfect sphere in true physical space. In the other, where dark energy is more complex, our observational view of that same void is distorted, stretched into an elliptical phantom that misrepresents its true nature. This forces a humbling realization. The grand architecture of the cosmic web, the very map we have painstakingly built of filaments and voids, may be a distorted reflection. To find the true structure of the universe, we must first learn to see through the illusion of time itself. The grandest structures in the cosmos began as the smallest possible whispers. Those colossal voids and superclusters, stretching for hundreds of millions of light years, owe their existence to a quantum event in the first trillionth of a second after the Big Bang. During that fleeting moment, the entire universe underwent a period of hyper-expansion called inflation, stretching from subatomic size to something vastly larger. And according to our best theories, the vacuum of space during this violent growth was not perfectly smooth. It was a seething quantum foam where pairs of virtual particles flickered in and out of existence. These were the primordial quantum fluctuations, tiny, random hills and valleys in the density of the universe, born from pure uncertainty on a subatomic scale. Inflation acted like a cosmic magnifying glass, stretching these infinitesimal wrinkles across the entire sky. A region that was ever so slightly denser than its surroundings would, over billions of years, pull in more and more matter through gravity, eventually becoming a supercluster of galaxies. A region that was slightly less dense would see matter flow away, destined to become a cosmic void. The entire cosmic web of structure we see today is a frozen fossil of these quantum ripples, written across the sky on a scale of unimaginable vastness. But how do we know this is more than just a compelling story? The evidence is etched into the oldest light we can see. The cosmic microwave background shows us a snapshot of the universe at 380,000 years old, and it is not perfectly uniform. It is mottled with tiny temperature variations, hot spots and cold spots that correspond directly to those ancient density fluctuations. This pattern is the blueprint for all future structure. Yet this blueprint has a very specific signature, a preferred scale woven into the fabric of the cosmos. This signature is known as baryon acoustic oscillations. In the first few 100,000 years, the universe was a hot, dense plasma of atomic nuclei, electrons, and light. Pressure waves, much like sound waves, rippled through this primeval soup. The photons and matter were locked in a tight dance, with radiation pressure pushing matter outward from any dense region. Then, as the universe cooled, atoms formed in an event called recombination. The photons suddenly broke free, streaming across the universe to become the cosmic microwave background we observe today. The matter, no longer pushed by radiation, was frozen in place. This process created a fundamental cosmic ruler: the distance those sound waves could travel before the universe became transparent became a standard size, about 500 million light-years across. We see its imprint everywhere. If you were to take a vast census of galaxies, you would find a subtle but statistically significant tendency for pairs of galaxies to be separated by this specific distance. It is as if the universe has a faint echo, a ghostly ring in the distribution of matter. This same oscillation scale is visible in the distribution of the voids themselves. They are not randomly sized. There is a most likely diameter for these great empty spaces, a scale set by those primordial sound waves. Animations of the universe's evolution show this beautifully. They start with a nearly smooth, foggy expanse, tinted with the faint red and blue patches of the infant cosmic microwave background. Then, gravity begins its slow, relentless work. The blue, underdense regions expand and empty out, becoming vast spherical voids. The red, overdense regions contract, collapsing into the brilliant filaments and knots of the cosmic web. Over billions of years, this web clarifies, with voids merging and growing as filaments thin and stretch. The largest structures we see today are not random accidents. They are the final, majestic outcome of a process that began with quantum noise, sculpted by the physics of primordial sound and the relentless pull of gravity. This grand pattern raises a profound question. Are the rules that govern the birth of our universe the only possible rules, or is the cosmic web we see just one possible outcome in a much wider multiverse of possibilities? The faint, all-pervasive glow of the cosmic infrared background is the universe's collective memory of its first light. This diffuse radiation, a blanket of heat that fills the entire sky, is the summed emission from every star and galaxy that has ever shone, their light stretched by the expansion of the universe into the infrared part of the spectrum. But when we try to account for all the sources of this light, we find a puzzle. The known galaxies we can see do not produce enough infrared light to explain the entire background glow. A significant portion of this cosmic warmth is missing its origin story. One of the most compelling and challenging possibilities is that the voids themselves are contributing to this ghostly light. Within the vast emptiness, the first generation of stars and the earliest, faintest dwarf galaxies could have formed in near total isolation. Their brilliant, short lives would have produced immense amounts of ultraviolet and optical light. Over billions of years, the relentless expansion of the cosmos has stretched this ancient starlight, redshifting it down into the infrared wavelengths we now detect as the background glow. The dust that formed around those early stars would have absorbed their light and re-radiated it as infrared, a process that makes the signal even stronger. The contribution from voids is especially important because these regions are so pristine. Without the pollution and interference from later generations of stars, the light from the very first stellar populations could have escaped into intergalactic space more easily, creating a clean, diffuse signal that now permeates the great nothingness. Disentangling this specific whisper from the cosmic chorus is one of astronomy's most delicate tasks. The problem is that the infrared background is a composite of countless sources. The brilliant glow from nearby galaxies, the faint heat from distant, dusty star-forming galaxies, and even the zodiacal light from dust within our own solar system all blend together into a single, confusing fog. To find the void's contribution, scientists must perform a kind of cosmic subtraction. They take a deep image of a known, massive void and carefully remove the light from every single galaxy they can identify, no matter how faint. What remains should be a smooth, residual glow, the direct infrared light from the unseen first stars and the dust they enriched within the void. Composite images of the cosmic infrared background reveal this beautifully. Vast, colorful maps of the entire sky show a mottled, uneven glow, with some of the faintest patches corresponding remarkably well with the locations of known supervoids. Annotations on these images point to these dark regions, highlighting them not as places of total emptiness, but as potential reservoirs of this lost light. This faint signal, if it can be confirmed, would be a direct window into the era of the very first stars. It would tell us that star formation, even in the most barren corners of the cosmos, began earlier and was more widespread than we ever thought. The voids are not just empty space, they are a canvas upon which the universe's first dawn was painted, and their lingering warmth is the final, fading echo of that ancient fire. That profound emptiness is an illusion of our limited perception. While our telescopes reveal a near-total void, theoretical models predict a hidden ecosystem thriving in the darkness. Within these vast expanses, astronomers expect to find a sparse population of faint dwarf galaxies, countless dark matter mini-halos, and immense, diffuse clouds of primordial gas. These are the ghosts of the cosmic web, structures so tenuous they barely register against the overwhelming black. Detecting them pushes our technology to its absolute limits. The dwarf galaxies in voids are often little more than smudges of old red stars, lacking the vibrant blue glow of new star formation. They are so dim that they blur into the background noise of the sky, their light drowned out by the glare of our own atmosphere and the instrumental limits of even our greatest observatories. The dark matter substructure is even more elusive. These mini-halos are clumps of pure dark matter, lacking any stars or gas to illuminate them. They reveal their presence only through their subtle gravitational influence, bending the light of more distant galaxies in a phenomenon known as weak gravitational lensing. But in the void, where everything is so sparse that lensing signal is incredibly faint, a whisper of distortion in an already faint image, the diffuse gas clouds, potential remnants of the universe's first structures, are perhaps the most challenging to observe. They do not glow with their own light. Instead, we must rely on the rare occasion that the light from a distant quasar passes directly through one of these clouds. As the light travels through the cloud, specific elements in the gas, like hydrogen or helium, absorb very precise wavelengths, leaving a faint, telltale dip in the quasar spectrum. It is like trying to identify a specific, invisible cloud in the Earth's atmosphere by analyzing the precise color of sunlight filtered through it from a single star trillions of miles away. Future observatories promise to lift this veil. The James Webb Space Telescope, with its infrared eyes, can peer through cosmic dust to see the faint, red glow of the earliest dwarf galaxies. The upcoming Nancy Grace Roman Space Telescope will conduct vast sky surveys, mapping the distribution of billions of galaxies and, through statistical analysis, revealing the underlying scaffold of dark matter mini-halos by the way they warp the space around them. Advanced radio telescopes will hunt for the faint spectral signatures of hydrogen in these primordial clouds. Detailed supercomputer simulations show us what we are missing. They visualize a seemingly empty void not as a blank sphere, but as a complex hierarchical structure. The void is filled with a web of dark matter, a tracery of fine filaments connecting tiny, invisible halos. Along these filaments, a few lonely dwarf galaxies drift like isolated islands, vast, billowing clouds of gas, the raw, unpolluted material of the early universe, hang motionless in the dark. This hidden architecture has profound implications. If we find that voids are filled with these predicted mini-halos, it would strongly support the cold dark matter model, which predicts such small-scale structure. If, however, the voids are smoother and emptier than the models allow, it might force us to reconsider the very nature of dark matter, perhaps suggesting it is warmer and more fast-moving, preventing such small clumps from forming. For galaxy formation, discovering a population of pristine, unchanged dwarf galaxies in the voids would be like finding living fossils. These galaxies, isolated from the chaotic mergers and interactions of the crowded clusters, could preserve the conditions of the early universe, showing us what the very first galaxies were like. The great cosmic voids are not deserts, they are wildernesses, and we are only now developing the tools to see the subtle life that calls them home. These vast, silent voids may have been the very channels through which the first light of creation escaped. During the epoch of reionization, the universe transformed from a dark, opaque fog of neutral hydrogen into the transparent cosmos we see today. This monumental shift was powered by the first stars and galaxies, whose fierce ultraviolet radiation blasted apart the hydrogen atoms, stripping away their electrons and ionizing the gas. But how did this light, born in isolated pockets, manage to permeate the entire universe so completely? The cosmic voids likely served as cosmic shortcuts. In the crowded regions of the early universe, dense knots of neutral gas would have absorbed this ionizing radiation quickly, slowing its progress. But within a void where matter was sparse, there was simply less hydrogen to ionize. A single brilliant source on the edge of a void could flood that entire empty volume with ultraviolet light, creating a vast, growing ionization bubble. These bubbles would have merged and connected, their pathways through the voids allowing light to travel incredible distances and eventually burn away the universal fog. Think of it like a wildfire spreading through a dense forest versus an open plain. In the forest, the fire advances slowly, consuming each tree in its path. But on the plain, the flames race ahead unchecked. The voids were those open plains for the first light of the universe. Conversely, some of the deepest, most isolated voids might have been the last holdouts of neutrality. As ionization fronts swept through the cosmos, these profound emptinesses, devoid of any ionizing sources, could have remained as dark pockets of pristine hydrogen, the final regions to be illuminated. We can actually probe this ancient era by studying the ghosts of that primordial gas. When astronomers point their telescopes at the light of a distant quasar, they are looking back in time. As that light journeys for billions of years to reach us, it passes through clouds of neutral and ionized hydrogen. Each cloud imprints a specific dark line on the quasar spectrum, a pattern known as the Lyman alpha forest. In regions that were ionized early, the forest of lines is thin because most of the hydrogen has been cleared away. But in spectra that have passed through a region that was slow to ionize, the forest is dense and tangled. By mapping these patterns, scientists can essentially create a chart of the ionization history of the universe, pinpointing where the voids acted as clear channels and where they served as the last neutral frontiers. Visualize the early universe as a sea of dark purple fog. Suddenly, pinpricks of intense blue light appear, the first stars and galaxies. Around them, spherical bubbles of clear, ionized space begin to grow. These bubbles expand fastest where the cosmic density is lowest, racing through the voids and merging with other bubbles. The filaments of the cosmic web, dense with gas, are the last to clear, glowing faintly as they are finally eaten away by the advancing light. The voids were not just passive bystanders in this cosmic dawn. They were active participants, their profound emptiness sculpting the very path of light and helping to build the transparent universe we call home. What other secrets of our genesis are encoded in the silent architecture of these great nothings? Gravity's lens works in reverse within the cosmic void. We are accustomed to the idea that massive objects like galaxy clusters bend and magnify the light from more distant galaxies, creating brilliant arcs and multiple images. But in the profound emptiness of a void, something far stranger occurs. Instead of focusing light, the void acts as a negative lens, causing the images of background galaxies to appear subtly stretched and distorted outward, a phenomenon known as demagnification. This is because a void is not just empty space, it is a region of lower than average density, a gravitational valley. light rays passing through this valley experience less gravitational pull than they would in the average universe, causing them to diverge slightly rather than converge. The effect is incredibly subtle, a distortion of less than 1%, but across the vast expanse of a supervoid, it becomes statistically detectable. We do not see dramatic arcs. Instead, we see a coherent, whisper-thin pattern of distortion in the shapes of millions of faint background galaxies, all subtly stretched in a direction that seems to flow away from the void's center. This weak gravitational lensing is one of the most powerful tools we have to weigh the void itself. By meticulously measuring the precise amount of this cosmic stretching, astronomers can map the void's total mass distribution, including the contribution from its unseen dark matter scaffold. The results have been surprising. The lensing signal suggests that even these great emptinesses contain more mass than their visible galaxies alone can account for, confirming that dark matter permeates the voids as a faint, all-encompassing web. This technique also probes the nature of dark energy. The rate at which voids grow and evolve is dictated by the competition between gravity, which tries to pull matter back in, and dark energy, which pushes it apart. By measuring the lensing distortion of voids at different distances, and therefore different cosmic epochs, we can trace how this competition has played out over billions of years. Does the demagnification effect match our models of a universe driven by a constant dark energy? Or does it suggest something more dynamic? The data is still coming in, but each new measurement sharpens our view. Picture two images side by side. On one side, a massive galaxy cluster acts as a natural telescope, warping the light of a distant blue galaxy into a perfect, bright Einstein ring. On the other, a map of a cosmic void shows not a ring, but a vast circular pattern of tiny, elongated galaxy shapes, all oriented tangentially, as if being pushed away from the center of nothing. This demagnification is the void's signature, a faint imprint of its gravitational fingerprint on the fabric of space-time. It reveals that even the great nothings have a measurable pull, or rather, a measurable lack of it, bending the cosmos in their own unique way. This great cosmic push and pull may be distorting our most fundamental measurement of the cosmos. Astronomers are locked in a quiet but profound conflict over the Hubble constant, the number that describes how fast the universe is expanding today. The problem is stark. When we measure the expansion using the ancient light of the cosmic microwave background, which shows the infant universe, we get one value. But when we measure it using relatively nearby supernova and other local markers, we get a consistently faster rate. This discrepancy is known as the Hubble tension, and it suggests a fundamental flaw in our cosmic accounting. The early universe measurement acts as a prediction for what the expansion rate should be today, based on our standard model of cosmology. The local measurement is a direct observation of what it actually is. They do not match. Graphs illustrating this tension are striking. One line, representing the pristine early universe data from the CMB, points to a specific, slower expansion rate. Another line, built from thousands of supernova observations in the local universe, points clearly to a faster one. The gap between them is too large to be a simple error. It is a genuine crisis. This is where the silent influence of cosmic voids might be playing a decisive role. Our local region of the universe is not perfectly average. We reside in a relative cosmic metropolis, but one that is flowing toward the great attractor and away from the dipole repeller. These vast bulk flows, rivers of galaxies driven by the gravitational push of voids and the pull of superclusters, mean our neighborhood is in motion relative to the overall expansion of the universe. If we are caught in a faster-than-average current, our local measurements of the Hubble constant could be skewed. We might be mistaking this peculiar motion for a genuinely faster global expansion. Think of it like trying to measure the flow of a wide, calm river while you are sitting in a small boat that is being swept along by a local, faster current. Your measurement of the river's speed would be artificially high. Cosmic voids, through their collective gravitational influence, could be creating these deceptive local currents. The implications are staggering. If the Hubble tension is resolved by better accounting for these voids and flows, it would affirm our standard model of cosmology, a model built on dark matter and dark energy. It would mean we simply need a more precise map of our local cosmic geography. But if, after all that, the tension remains, it points to something far more exciting. We may need new physics. Perhaps dark energy is not a constant but is evolving, growing stronger over time. Maybe gravity itself behaves differently on the largest scales, or a new type of relativistic particle from the early universe is altering the cosmic expansion history. The great voids are not just empty spaces. They are the architects of cosmic flows, and their subtle push may be the key to understanding whether our universe is exactly as we believe, or if we are on the verge of a revolution that will redefine reality itself. This profound emptiness might be our best window into the very fabric of reality, deep within the cosmic void where the grip of matter and gravity is at its weakest. The true quantum nature of spacetime could be laid bare. At scales a billion trillion times smaller than an atom, the smooth, continuous universe we know may dissolve into a seething, chaotic froth. Physicists call this theoretical foundation quantum foam. It is a turbulent ocean where tiny wormholes might flicker in and out of existence, and the very concepts of before and after lose their meaning. In this realm, spacetime is not a static stage but a dynamic, dancing entity, constantly bubbling with virtual particles and microscopic black holes. Under normal conditions, this frantic activity is completely hidden from us, its effects vanishingly small. But in the immense, quiet expanse of a cosmic void, where a particle can travel for hundreds of millions of years without a single collision, the subtle influence of this foam might finally become detectable. The idea is that as light journeys across these vast distances, the frothy texture of spacetime would cause tiny, random jitters in its path. A single photon traversing a void does not travel a perfectly straight line. It is constantly buffeted by the quantum turbulence beneath it. Over a journey of a billion light years, these minuscule deflections could add up, causing the light to arrive at our telescopes slightly scrambled. For a sharp, pinpoint image of a distant galaxy, this scrambling would be negligible, but for the most violent and brief events in the universe, it could be the key to a discovery. Consider a gamma-ray burst, a colossal explosion that unleashes a flash of high-energy light in a fraction of a second. The different photons in that flash, despite having slightly different energies, should all travel at the same speed, the speed of light. If spacetime is smooth, they will all arrive at the same time after their epic journey. But if spacetime is foamy, the higher energy photons might interact with the turbulence more strongly, causing a tiny, calculable delay. It is like watching a group of runners sprint across a perfectly flat field versus a field riddled with invisible, popping bubbles. On the flat field, they finish together. On the foamy field, the heavier, more powerful runners might be slowed down just a fraction more. Scientists have spent years analyzing the light from distant gamma-ray bursts and other brilliant phenomena, searching for these telltale energy-dependent delays. So far, the results have been a resounding silence. Spacetime appears incredibly smooth, even across the largest voids, but this null result is in itself a profound discovery. It places severe constraints on the possible theories of quantum gravity, ruling out the most dramatic models of a churning, chaotic cosmos. The search continues, pushing into ever higher energies and ever greater distances. Could the ultimate theory of everything be written not in the crowded centers of galaxies, but in the silent, quantum whispers of the void? The answer may be hiding in the next brilliant flash from the deepest dark, a message from the foam from which all reality is spun. The silent expansion we measure today is only a prelude to an unimaginable final act. In a cosmos ruled by dark energy, the great voids are not just growing, they are destined to become the universe itself. Picture a time lapse of the cosmos spanning trillions of years. Initially, the cosmic web is a brilliant, intricate tapestry of glowing filaments and dense clusters. But dark energy's relentless push never ceases. The voids begin to swell, their boundaries pressing inward on the thinning strands of the web. Neighboring voids touch, then merge, their combined emptiness creating ever larger spheres of nothingness. The filaments, stretched too thin, begin to snap. Island galaxies, once part of a grand metropolis, are cut adrift. Over an almost endless span of time, the last bridges of light are severed. The cosmic web, the grand structure born from quantum whispers, dissolves completely into a single, all-encompassing void. This is the universe's trajectory toward heat death, a state not of fire, but of absolute cold and uniformity. In this distant era, any observer left in our local group would witness a profoundly lonely sky. One by one, the galaxies beyond our own gravitationally bound neighborhood would redden, then fade from view entirely. Their light, stretched by the accelerating expansion beyond the visible spectrum, would simply vanish. The universe beyond our doorstep would retreat behind a cosmic horizon, leaving only an impenetrable, eternal blackness. What does this mean for the structures we see today? The great superclusters and brilliant knots of galaxies are temporary, cosmic blooms that will inevitably wither. They are fleeting patterns in a slow-motion tide of emptiness. The voids, which seem like the backdrop today, are in fact the final victors in the cosmic contest. Their ultimate fate is to inherit everything, to become the dominant and eventually the only environment. This is a universe fading not with a bang, but with a slow, inexorable sigh into absolute stillness. The grand architecture collapses not from violence, but from a simple, unstoppable thinning. It is a philosophical revelation as much as a physical one. All that we hold as permanent, the vast constellations of galaxies, are merely transient glitter on the surface of a deepening dark. What legacy remains when the last structures dissolve into the final, eternal void? Our own cosmic address might be far more unusual than we ever suspected. The final mystery brings the vast scale of the cosmic void directly to our doorstep, asking a deeply unsettling question. Could the Milky Way itself be floating in a void? Astronomers call this the KBC void, named for the scientists who proposed it, and the evidence is surprisingly compelling. When we map the large-scale structure in our immediate cosmic neighborhood, we find that the density of galaxies around us is significantly lower than the universal average. We appear to reside in a local underdensity, a bubble of relative emptiness stretching for hundreds of millions of light years. This is not a perfect vacuum, of course, but a region where the glittering cities of galaxy clusters are fewer and farther between. This discovery has a profound consequence. If we are living inside a giant void, our measurements of the universe's expansion rate, the Hubble constant, could be systematically skewed. From within this underdense region, the local gravitational landscape is different. The weaker pull of the surrounding void might allow galaxies to flow outward from us slightly faster than they would in an average part of the cosmos. We could be mistaking this local motion for a genuinely faster global expansion, potentially explaining a part of the troubling Hubble tension. This idea strikes at the heart of a foundational principle of cosmology, the Copernican principle. It states that we do not occupy a special or privileged place in the universe, but if we are sitting in one of the largest cosmic voids, then our vantage point is in fact highly unusual. Our entire view of the cosmos is filtered through this lens of local emptiness. Picture a zoom-out sequence starting from our pale blue dot. We pull back from Earth past the Moon, the Solar System, and the familiar spiral arms of the Milky Way. Our galaxy then becomes just one member of the local group, which itself is a small part of the Virgo supercluster, but the journey does not stop there. We continue to pull back, and the Virgo supercluster reveals itself to be merely a single, thin filament on the edge of an immense spherical emptiness, the local void. We are not at the center of the universe, but we may very well be living on the shores of a great cosmic nothing. This realization reframes our entire cosmic context. The profound silences and the great emptinesses we have explored are not just distant curiosities. They are part of our immediate environment, shaping our most fundamental observations. The universe's grandest mysteries are not only out there in the deepest dark. They surround us, they define our perspective, and they challenge our deepest assumptions about reality itself. We have journeyed across 25 of the cosmos's most profound enigmas, from the silent expanse of the Boötes Void to the quantum whispers of spacetime itself. Each mystery reveals that what we call empty is anything but. The cosmic void is not a barren wasteland. It is a dynamic frontier, a treasure trove of scientific puzzles that continually push the boundaries of our knowledge. These great nothings challenge our understanding of gravity, hide the universe's missing matter, and may even hold windows to other realities. They are the ultimate laboratories for testing our most fundamental theories about the nature of reality. The journey does not end here. Our exploration is accelerating, powered by a new generation of eyes on the cosmos. The James Webb Space Telescope peers into the deepest voids, hunting for the faint glow of the first stars. The Vera C. Rubin Observatory will soon begin its monumental scan of the sky, mapping billions of galaxies to trace the invisible architecture of dark matter and the subtle growth of these great emptinesses. These instruments are not just tools, they are extensions of our deepest curiosity, our drive to comprehend the vast and mysterious universe we call home. This quest to find meaning in the silence and structure in the void is one of humanity's most noble endeavors. We are a species born on a tiny rock, daring to map the infinite. So we turn the question to you, of these 25 cosmic riddles, which one captivates your imagination the most? Was it the phantom push of the dipole repeller, the chilling alignment of galaxy spins, or the possibility of a bubble universe collision? Share your favorite mystery in the comments below and subscribe to join us as we continue our deep dives into the universe's greatest enigmas. The cosmos